Chapter 12 of The Story of Alchemy. This LibriVox recording is in the public domain. Recording by Peter Yearsley. The Story of Alchemy and the Beginnings of Chemistry by M. Pattison Muir. Chapter 12. The recognition of chemical changes as the interactions of definite substances. The experimental study of combustion made by Lavoisier proved the correctness of that part of Stahl's phlogistic theory which asserted that all processes of combustion are very similar, but also proved that this likeness consists in the combination of a distinct gaseous substance with the material undergoing combustion, and not in the escape therefrom of the principle of fire, as asserted by the theory of Stahl. After about the year 1790, it was necessary to think of combustions in the air as combinations of a particular gas or air with the burning substances, or some portions of them. This description of processes of burning necessarily led to a comparison of the gaseous constituent of the atmosphere which played so important a part in these processes, with the substances which were burned. It led to the examination of the compositions of many substances, and made it necessary to devise a language whereby these compositions could be stated clearly and consistently. We have seen in former chapters the extreme haziness of the alchemical views of composition, and the connections between composition and properties. Although Boyle had stated very lucidly what he meant by the composition of a definite substance, about a century before Lavoisier's work on combustion, nevertheless the views of chemists concerning composition remained very vague and incapable of definite expression, until the experimental investigations of Lavoisier enabled him to form a clear mental picture of chemical changes as interactions between definite quantities of distinct substances. Footnote: Boyle said in 1689, "I mean by elements certain primitive and simple or perfectly unmixed bodies, which, not being made of any other bodies, or of one another, are the ingredients of which all those called perfectly mixed bodies are immediately compounded, and into which they are ultimately resolved." End footnote. Let us consider some of the work of Lavoisier in this direction. I select his experimental examination of the interactions of metals and acids. Many experimenters had noticed that gases, or airs as they were called up till near the end of the 18th century, are generally produced when metals are dissolving in acids. Most of those who noticed this said that the gases came from the dissolving metals. Lavoisier said they were produced by the decomposition of the acids. In order to study the interaction of nitric acid and mercury, Lavoisier caused a weighed quantity of the metal to react with a weighed quantity of the acid, and collected the gas which was produced. When all the metal had dissolved, he evaporated the liquid until a white solid was obtained. He heated this solid until it was changed to the red substance called at that time red precipitate, and collected the gas produced. Finally, Lavoisier strongly heated the red precipitate. It changed to a gas, which he collected, and mercury, which he weighed. The weight of the mercury obtained by Lavoisier at the end of this series of changes was the same, less a few grains, as the weight of the mercury which he had caused to react with the nitric acid. The gas obtained during the solution of the metal in the acid, and during the decomposition of the white solid by heat, was the same as a gas which had been prepared by Priestley, and called by him nitrous air, and the gas obtained by heating the red precipitate was found to be oxygen. Lavoisier then mixed measured volumes of oxygen and nitrous air, standing over water. A red gas was formed and dissolved in the water, and Lavoisier proved that the water now contained nitric acid. The conclusions regarding the composition of nitric acid drawn by Lavoisier from these experiments was that nitric acid is nothing else than nitrous air, combined with almost its own volume of the purest part of atmospheric air, and a considerable quantity of water. Lavoisier supposed that the stages in the complete reaction between mercury and nitric acid were these: the withdrawal of oxygen from the acid by the mercury, and the union of the compound of mercury and oxygen thus formed with the constituents of the acid which remained when part of its oxygen was taken away. The removal of oxygen from nitric acid by the mercury produced nitrous air. When the product of the union of the oxide of mercury and the nitric acid, deprived of part of its oxygen, was heated, more nitrous air was given off, and oxide of mercury remained, and was decomposed at a higher temperature into mercury and oxygen. Lavoisier thought of these reactions as the tearing asunder by mercury of nitric acid into definite quantities of its three components, themselves distinct substances, nitrous air, water, and oxygen, and the combination of the mercury with a certain measurable quantity of one of these components, namely oxygen, followed by the union of this compound of mercury and oxygen with what remained of the components of nitric acid. Lavoisier had formed a clear, consistent, and suggestive mental picture of chemical changes. He thought of a chemical reaction as always the same under the same conditions, as an action between a fixed and measurable quantity of one substance, having definite and definable properties, with fixed and measurable quantities of other substances, the properties of each of which were definite and definable. Lavoisier also recognized that certain definite substances could be divided into things simpler than themselves, but that other substances refused to undergo simplification by division into two or more unlike portions. He spoke of the object of chemistry as follows: "In submitting to experiments the different substances found in nature, chemistry seeks to decompose these substances and to get them into such conditions that their various components may be examined separately. Chemistry advances to its end by dividing, subdividing, and again subdividing, and we do not know what will be the limits of such operations. We cannot be certain that what we regard as simple today is indeed simple. All we can say is that such a substance is the actual term whereat chemical analysis has arrived, and that with our present knowledge we cannot subdivide it." Footnote: I have given a free rendering of Lavoisier's words. End footnote. In these words Lavoisier defines the chemical conception of elements. Since his time an element is the actual term whereat chemical analysis has arrived. It is that which, with our present knowledge, we cannot subdivide. And as a working hypothesis, the notion of element has no wider meaning than this. I have already quoted Boyle's statement that by elements he meant certain primitive and simple bodies not made of any other bodies or of one another. Boyle was still slightly restrained by the alchemical atmosphere around him. He was still inclined to say, "This must be the way nature works. She must begin with certain substances which are absolutely simple." Lavoisier had thrown off all the trammels which hindered the alchemists from making rigorous experimental investigations. If one may judge from his writings, he had not struggled to free himself from these trammels, he had not slowly emerged from the quagmires of alchemy, and painfully gained firmer ground. The extraordinary clearness and directness of his mental vision had led him straight to the very heart of the problems of chemistry, and enabled him not only calmly to ignore all the machinery of elements, principles, essences, and the like, which the alchemists had constructed so laboriously, but also to construct, in place of that mechanism which hindered inquiry, genuine scientific hypotheses which directed inquiry, and were themselves altered by the result of the experiments they had suggested. Lavoisier made these great advances by applying himself to the minute and exhaustive examination of a few cases of chemical change, and endeavouring to account for everything which took part in the processes he studied, by weighing or measuring each distinct substance which was present when the change began, and each which was present when the change was finished. He did not make haphazard experiments. He had a method, a system. He used hypotheses, and he used them rightly. "Systems in physics," Lavoisier writes, "are but the proper instruments for helping the feebleness of our senses. Properly speaking, they are methods of approximation, which put us on the track of solving problems. They are the hypotheses which, successively modified, corrected, and changed by experience, ought to conduct us some day, by the method of exclusions and eliminations, to the knowledge of the true laws of nature." In a memoir wherein he is considering the production of carbonic acid and alcohol by the fermentation of fruit juice, Lavoisier says, "It is evident that we must know the nature and composition of the substances which can be fermented, and the products of fermentation. For nothing is created, either in the operations of art or in those of nature, and it may be laid down that the quantity of material present at the beginning of every operation is the same as the quantity present at the end, that the quality and quantity of the principles are the same, and that nothing happens save certain changes, certain modifications. On this principle is based the whole art of experimenting in chemistry. In all chemical experiments we must suppose that there is a true equality between the principles of the substances which are examined and those which are obtained from them by analysis. Footnote: Lavoisier uses the word principle here and elsewhere to mean a definite homogeneous substance. He uses it as synonymous with the more modern terms element and compound. End footnote. If Lavoisier's memoirs are examined closely, it is seen that at the very beginning of his chemical inquiries he assumed the accuracy and the universal application of the generalization, nothing is created either in the operations of art or in those of nature. Naturalists had been feeling their way for centuries towards such a generalization as this. It had been in the air for many generations. Sometimes it was almost realized by this or that investigator, then it escaped for long periods. Lavoisier seems to have realized, by what we call intuition, that however great and astonishing may be the changes in the properties of the substances which mutually react, there is no change in the total quantity of material. Not only did Lavoisier realize and act on this principle, he also measured quantities of substances by the one practical method, namely by weighing, and by doing this he showed chemists the only road along which they could advance towards a genuine knowledge of material changes. The generalization expressed by Lavoisier in the words I have quoted is now known as the law of the conservation of mass. It is generally stated in some such form as this: the sum of the masses of all the homogeneous substances which take part in a chemical or physical change does not itself change. The science of chemistry rests on this law. Every quantitative analysis assumes the accuracy and is a proof of the validity of it. Footnote: I have considered the law of the conservation of mass in some detail in Chapter 4 of The Story of the Chemical Elements. End footnote. By accepting the accuracy of this generalization and using it in every experiment, Lavoisier was able to form a clear mental picture of a chemical change as the separation and combination of homogeneous substances, for by using the balance he was able to follow each substance through the maze of changes, to determine when it united with other substances, and when it separated into substances simpler than itself. End of chapter 12.